Hey students, welcome to lecture number 10 of multiple zeta values and modular forms. So last time we finished section number 3, where we talked about families of linear relations among multiple zeta values, and in particular we talked about these Ono relations and these connected sums. And today we want to start with section number 4, where we will be interested in some connection of multiple zeta values and double zeta values. And for this we will start by talking about the formal double zeta space, which somehow can be seen as some space spanned by formal symbols which satisfy these double shuffle relations in Devs 2. And then later we will be interested in real objects which also satisfy these relations, and then we say that these real objects give a realization of this space. Okay, so again, what will be the motivation for this formal double zeta space? So in this section 3, where we talked about these extended double shuffle relations, we had a big family of linear relations which conjecturally gave all linear relations. And now we can ask the question, if you just take the extended double shuffle relations in Devs 2, meaning you consider the products Devs 1 times Devs 1, what do these double shuffle relations actually imply for multiple zeta values? So we want to understand these special cases of extended double shuffle relations. And then by just using these relations, we will be interested in what families of linear relations can we actually prove by just using this specific set of relations. And then we will be interested in real objects which satisfy these relations. So of course here one example for objects satisfying these relations are given by zeta values in Devs 2 in this case. But we will also see, so in Devs 1 we have a Riemann zeta value, and in Devs 2 we have these double zeta values. But we will also see that we will find a so-called realization of the space given by Eisenstein series, which we introduced in section 1. And then we will see that these relations, which can be obtained by these double shuffle relations in Devs 2, give some statements about modular forms. For example, we will see that any Eisenstein series is a polynomial in the Eisenstein series of weight 4 and weight 6. And we will also prove these so-called Ramanujan differential equations. And also we will obtain more results. And then we will also see next time that these relations among these modular forms will imply relations among double zeta values when we consider cusp forms. But today we will first start by introducing this formal double zeta space and then prove some relations in this formal space. But first let's recall what we mean here by double shuffle relations in Devs 2. So recall that if we had integers greater or equal to 2, then the product of two Riemann zeta values could be expressed by the Staffel product and also by the shuffle product. And this condition here ensured that these objects converge. But then we also saw that we can regularize this equation by introducing these Staffel and shuffle regularized multiple zeta values. And then the Staffel regularized multiple zeta values, they satisfied the Staffel product. And now we can allow these K1 and K2 also to be D1. And these were polynomials, so this is an equation of polynomials where the coefficients are given by multiple zeta values. And then we also saw when we take the shuffle here, so in Devs 1 these shuffle and Staffel regularized zeta values are the same, then we saw that they satisfy the shuffle product for all possible indices. But we also saw that these Staffel and these shuffle regularized zeta values are not the same, and in Devs 1, so in Devs 1 they are the same, but in Devs 2 we saw that there's this map rho, which was a map from the polynomial ring with real coefficients to the polynomial ring with real coefficients. And then we saw that this shuffle regularized multiple zeta value of some index t can be obtained from the Staffel regularized by applying this map rho to this polynomial. And then we also saw that this rho on 1 is just 1, the rho on the variable t is just t, so it doesn't change anything there. but starting with t squared gives t squared plus zeta 2. And so on. So we see that if these shuffle regularized multiple zeta values have some t squared in there, then the shuffle regularized multiple zeta value is the same up to some factor with zeta 2. And this just means that the only difference appears when the index here in def2 is just the index 1, 1, because all other indices just give monomials like this. So we see that the only difference in def2 between these two regularization is given by this one here, saying that zeta shuffle 1, 1 is zeta stuffle 1, 1 plus 1/2 zeta 2. And in particular this is 0, and therefore this stuffle regularized thing here is minus 1/2 zeta 2. Okay, so in one nice way to describe these relations is by considering their generating series. So these formulas look quite complicated. Well, in def2 it's not so extremely complicated, but already these binomial coefficients are kind of ugly. So one nice way to write these equations down is by considering their generating series. So this bullet is now either shuffle or stuffle, and then by tx we denote the generating series of the single zeta value, which is basically just zeta k, and in the case k equals 1, this is just t. And this t with x and y is the generating series of these double zeta values. And then, so let me go back here. So let's copy these equations and put them here. So here, this first line here corresponds to this equation here. So clearly on the left hand side we just have the product of the generating series in def1. And here changing k1 and k2 just means we change the variables x and y. And here the last part gives this term here, and this I want to make clear why. So if you write down what is this thing here, so by definition this is k greater or equal to 1, and then zeta k, well, bullet t, and then it's x k minus 1 minus y, k minus 1 x minus y. But this you can factor out here, and so you can write this as a sum k1, k2 greater or equal to 1. And then here you have zeta k1 plus k2, bullet t, and x1, k1 minus 1. Oops, no, not x1, just x. And here y, k2 minus 1. So this is because this is just the sum of these monomials with k1 plus k2 equals k. And therefore you can write this sum like this. And therefore if you look at the coefficient in this equation of x to the k1 minus 1 and y to the k2 minus 1, you get exactly this equation here. And also this equation here. So these binomial coefficients come into play when you do this change of variables here in the generating series. And now these extra terms, so here this is a Kronecker delta, this means this extra term here just appears if we consider the generating series of the shuffle regularized multiple zeta values. And here we have this extra term if we consider the stuffle regularized multiple zeta values. And this comes from the fact that we have this difference here. Maybe I leave it. So here. So we have this equation here, and if I replace the shuffle by the stuffle plus 1/2 zeta 2, then in the case when j is 1, and this is also 1, then I get one extra term, this 1/2 zeta 2 twice, and therefore the constant term in this equation here, because constant term means that k1 and k2 equals to 1, then I need to add this extra term here. And also if I replace this stuffle here by the shuffle regularized, then I would have a minus 1/2 zeta 2 there, and therefore, because I get it twice here, I get minus 1 times zeta 2. Okay. So now, so we have these double zeta values, so these are real numbers and they satisfy these equations here. And now we want to consider a vector space spanned by formal symbols, which somehow corresponds to these double zeta values, these single zeta values, and these products. For all three types we will introduce a formal symbol, and then we consider the span by these symbols modulo these relations. And this is what we will call the formal double zeta space. So again, the formal double zeta space is defined as the Q-span of these formal symbols zk, zk1, k2, pk1, k2, and then we divide out this relation here. So these symbols pk1, k2 you can think of being, they correspond to the product, and these zk1, k2 correspond to the double zeta value, and these zk correspond to the single zeta value. So you see we have exactly the same relations as before, but this is now for k1 and k2 greater equal to 1. But the only difference is that in the case k1 and k2 equal to 1, we don't put this extra term here. And you will also see in a minute that this has some consequences in weight 2. But besides weight 2, this is exactly the same relations as we have for zeta values. And also notice by this relation here that this pk here in the definition can always be written in terms of these zk and k1, k2, because if you look at this equation here, you could also just define this formal double zeta space as a span of these symbols modulo these relations, because this pk doesn't give any new information here, but we will want to keep this pk in there because we will see later that we can write down relations in this space in a nicer form if we also have this extra symbol pk, and also in the real world this pk should be think of being a product. But one important point here is that in this formal setup this pk is not a product, it's just a symbol, and we consider the vector space spanned by these symbols, because we will see that in the case when we consider Eisenstein series, then this zk will correspond to the Eisenstein series of weight k, this zk1, k2 will correspond to some double Eisenstein series, but this pk will not be exactly the product of Eisenstein series. In most cases it will be the product, but we will have some extra terms. And therefore, in this setup, we don't want this p to be actually a product, and we just want this to be a formal symbol, because otherwise we wouldn't get some applications for modular forms later. Okay, but now, so we have this vector space here, defined by the span of these formal symbols, modulo these relations. So the first question we can ask is, what is the dimension of this space? So if we look at these relations, so how many generators have we? So the number of generators, well, so by this statement here, of course these zk1, k2 and zk, they span the space because pk can be written by these. And among these generators we have these relations here. And this equation here is symmetric in k1 and k2. So first of all, how many generators do we have? We have k generators, so we have zk, z1, k minus 1, up to zk minus 1, 1. So these are k. And how many relations do we have? Well, the relations, this set of relations, because it's symmetric in k1 and k2, is at least k half. And well, this is the case for k even, and for k odd we need to take the floor. But what we can see from this is that in the weight, if k is even, then the dimension of the space dk is bounded below by k half, because it could be that these relations are actually less than k half relations among these generators. And in the weight odd case, we have that the dimension is bounded below by k plus 1 half. And this is just because we have these k generators and we have these k half relations. But it could be that some of these relations are linearly dependent, meaning that they don't really give k half different relations. But the maximum of relations is k half, and therefore the dimension cannot be bigger than these bounds here. But we will actually see that we, in both cases here, have equality, and this we will actually prove today for the odd case, and maybe in next time we will prove it for the even weight case. Okay, but first let's look at this formal double zeta space in small weights. So here it's a small table. So in weight 1, where there's no symbol p k1, k2 and z k1, k2, because I cannot add two numbers greater or equal to 1 which add up to 1. So in weight 1, this space is just spanned by this one symbol, and there are no relations, and therefore the dimension is 1. And now the important point here in weight 2, we have P11, Z2 and Z11. But if you look at these relations, for the case K1 and K2 equal to 1, one relation you get is that 2 always needs to be 0. And you can also see by the second equation here that P11 is 2 times Z11. So in this case, one possible basis is given by Z11 and the dimension is 1. And in weight 3, we get that Z21 is Z3. This comes from comparing this here in the case K1 equals 1 and K2 equals to 2. And we also have that Z12 can be written like this. So in other words, you can see that every element can be written as a linear combination of Z3 and P13. So, and they don't have a relation among each other, so the dimension is 2. And then you can go on. So I give you, in this weight 4 and weight 5, I give you all possible relations. And here in weight 4, we see a possible basis is again given by Z13 and Z31. So it's again similar to the weight 2 case by Z odd odd. So the dimension is 2. In weight 5, it's again the single zeta value and these products. And also if you wonder, so pk1, pk2 is the same as pk2, pk1, because here the right hand side here is symmetric in k1 and k2. So therefore in this table here, I just consider the case when k1 is smaller or equal to k2. So here in weight 5 we see one possible basis is given by Z5, P14, P23, and in weight 6 again a possible basis is given by these Z odd odd, so Z15, Z33 and Z51. So the observation here is on the right hand side we have exactly these dimensions here. And here we see that in even weight it seems that Z odd odd gives a basis, and in odd weight we see that this Zk and all possible products which are not equal give a basis. And this we will see is indeed true in general. Okay, so one way to work in this space, in this formal double zeta space, is also to consider the generating series. So here we will now consider the generating series of these double zeta, not double zeta waves, these symbols Zk1 and K2. So for fixed weight K, we take the sum over all K1 and K2 which add up to K, and then consider here the generating series of this symbol Zk1, K2. Then this Pk is this generating series of these symbols Pk1, K2, and this Rk is given by this symbol Zk times this polynomial here. And then we see that similar to this generating series for these double zeta values, that this equation, the defining equation for this formal double zeta space can be then written in terms of generating series like this, with the same argument before that this term here comes from there. And also that these binomial coefficients come here, but because we don't include this extra term, we don't have this correction term here for the constant term, because in our base here, this Z2, which would correspond to zeta 2, is always 0, so we don't have this here. Okay, so this setup we will use to prove relations in the space of this formal double zeta space. And after proving relations, we want to find real objects which satisfy these relations, and this is what we will call a realization. So assume we have some Q vector space A, then we define the A-valued points of this double zeta space in A to be the homomorphism from dk to A as Q vector spaces, and this just means, so this we can identify with a choice of elements in A to the k, so meaning if I have elements zk, zk1, k2 which satisfy these relations, meaning these relations here. So if they satisfy this, then I can define a corresponding pk1, k2 in the space A. And this corresponds to giving a homomorphism from the space dk by sending this zk to this corresponding element here, and this zk1, k2 to this element here, and this is pk1, k2 to corresponding element in A here. So this is not really an equality, but you can identify these two sets. And this is what we will call a realization. So again, a realization in some vector space A for this dk means I have these k elements in this vector space A which satisfy exactly these linear relations. And then, of course, our multiple zeta values, they give a realization, which we need to correct a little bit in weight 2. But so if we say that this pk1, k2, so in this case for the vector space A, we just take R, or we could also just say we take the space of multiple zeta values, where in this case here it's even RT, because we take these polynomials, but we could also set T to be 1. And then if we send this pk1, k2 to the product of the shuffle regularized zeta values, and this zk1 to the double zeta value, and then the zk to the zeta value, except for the weight k equals 2 case, because there we know that the z2 always needs to be 0, then we see that this gives a realization of the formal double zeta space. And this just follows from the fact that these generating series of these shuffle regularized double zeta values satisfy exactly this relation here. Okay. And if you wonder why shuffle here, it's because if we define this zk to be this one here, except for the k equals 2, then here in the shuffle regularized version of this generating series functional equation, this extra term here gets erased in this part here. Okay. So this is one realization, but later our goal will be later to find a realization when this A is given by Q series with rational coefficients, and then in this case the zk will get mapped to the Eisenstein series if k is not 2 and to 0 otherwise, and this pk will basically get sent to k2 will get sent to gk1 times gk2, but we will have some correction terms here. If, for example, k1 is 2, then we will have some 1/2 k2 and then some derivative of some Eisenstein series gk2 here. And also when k2 is 2, you will have some derivative here. So this shows that this pk is basically the product, but we shouldn't force this to be really the product of these z's, because in the application we want to do later, this is actually not a product. It's almost a product, but we have some correction terms here. Okay, so now we want to prove our first family of linear relation in this space dk. And again, every time we prove a linear relation in the space dk, of course, every realization then will also satisfy these relations. And the first thing we want to prove is the sum formula in this space. So for all weights k greater or equal to 2, we have that this the sum of these double z k1, k2, where the first entry is greater or equal to 2, equals this symbol zk. And then if the weight is even, we can even split this sum up here in the part where the first entry is even, and if we just take those, then this is 3/4 of zk, and if we take those where the first entry is odd, then this is 1/4 of zk. And of course, if we add these two sums, we get this, and therefore we get 1 times zk. And this theorem we can now prove nicely by using this description with a generating series. So let's prove this. So recall that we have this equation here for the generating series. So if we define this dx y to be the difference of this minus this, so we here have, the other way, so this minus this, so we take this part here minus this part here, and then because they are the same, this dxy is always 0, no matter what I plug in for this x and y. And so the proof of number 1 is then simply given by saying, well, 0 is given by d of something, and for example I can plug in 1 and 0, and if I write this out, so this is zk 1 0 plus zk 1 1 plus minus zk 1 0 minus zk 0 1 minus, and if I plug in here in this rk 1 and 0, then this just gives the symbol zk. And now first thing we see is that this part here cancels out, and this one here, well, what happens if we plug in 1 1 in the generating series? This just means we take the sum of all def2 objects, but we subtract something here, and this part here is exactly z1 k minus 1. So here this is the sum over all, so j goes from 1 to k minus 1, z j k minus 1, but we subtract the part where this j equals to 1, and therefore we just take the sum from 2 to k minus 1, and because this is 0, we get that this equals zk. So this gives a simple proof of this sum formula here. And to prove the second statement, so these even and odd parts, we consider that we have zeros again, d of something. So for this something I can take 1 and minus 1, and then if you plug in 1 and minus 1 here and write this out, you get that this is given by the sum of these z in def2, but here I have a minus sign, minus zk. So therefore, if I take 1/2 this equation here, and I add or subtract it to this equation here, then depending on if I add or subtract it, I will erase the even parts here, or I will erase the odd parts here. So we get that, for example, if I add this 1/2, so plus 1/2 d1 minus 1, then I get 2 times the ones where this j is even, and zj k minus j minus 3/2 zk, because here 1/2 this, and I subtract it there, I get 3/2. Therefore this is 0, and if I divide by 2 I get this 3/4 for this even part. And to prove the second part we just consider minus 1/2. And this gives the odd formula. This one here. Okay, so this gives a nice simple relation among these symbols in this formal double zeta space. And then, for example, using this realization for multiple zeta waves, we get that this relation is also true for the real objects multiple zeta waves. And also later, when we introduce other realizations, we can use this formula and see that this is also satisfied by these objects. Okay, so now another way to work on this space of this formal double zeta space is not only use these generating series, but also use an action of GL2Z on these generating series, because with this a lot of things we can write down in a quite simple way. So first I need to define, I want to define an action of GL2Z. So first, these objects we considered, these generating series, they were all polynomials of homogeneous degree k minus 2 in these variables x and y. And this space we want to call Vk. And on this space we now want to define a right action of GL2Z. So if I consider an element in GL2Z, a 2 by 2 matrix A, B, C, D. So this is a 2 by 2 matrix with integer entries and determinant plus minus 1. And then let's say I have an element f in this Vk, so a homogeneous polynomial of degree k minus 2. Then I want to say what I mean by that this gamma x on f, so this is again a polynomial, and this will be just defined by making this change of variables here. So it's ax plus by in the first variable and cx plus dy in the second. And then by this definition you can check that this gives a right action of GL2Z on the space of polynomials. And now, so this was the functional equation which was satisfied by this generating series of these objects in the formal double zeta space. So how can we write this equation now in terms of these of this action? So this can be written like this. So the statement is that this functional equation by using this action can be stated like this. So meaning that this pk is just the action of 1 minus epsilon, and of course I need to say what epsilon is. So here's a list of matrices which will appear again and again in the next lectures. So this epsilon here is just this matrix here. So if I apply an epsilon to some f, what I just do is I just interchange x and y. And therefore here, if I consider the action of 1 plus epsilon on these polynomials, then I see that the action of 1, which means just the identity matrix, is just zkxy, and the action of epsilon is given by changing x and y. And here we just have r. And also, what I forgot to mention is that this action of GL2Z on the space Vk, we extend to an action of the group ring ZGL2Z on this space. So meaning we consider formal linear combination of matrices, and then the action of this just means that I have 1 times this action of this matrix here, plus 1 time the action of this matrix here. And also later we will have some more complicated linear combination of matrices in this group ring, but it's just linearly extending this action of GL2Z on this space here. And here the second equation, this part here, so the statement is that this is given by T. So T is this matrix here, 1, 1, 0, 1. And if we let t act on some polynomial here, then we have x plus y, and here 0 y, so this is exactly this. And t epsilon, so t epsilon is just where you change this like this, 0, and then you can see the action of t epsilon is exactly this here. And these other matrices will appear in a second, but of course a well-known fact is that these matrices denoted S and T here, they generate SL to Z, and for example if I also include epsilon, then these would generate GL to Z. So any other matrices here could be expressed by just using these three matrices, but it's quite convenient to allow all of them for special purposes. So especially this matrix U here will appear later when we talk about period polynomials, and this delta will play a role in a second, and also this sigma here. Okay, so now we have this action of GL to Z on this space of polynomials, and with this we now want to prove a lemma which gives the relation among these elements in this formal double zeta space. And maybe on the first sight this lemma looks a little bit complicated, but we will see that this actually gives a really nice statement for this formal double zeta space, and then also for the real objects given by double zeta values. So the statement of the lemma is the following. So recall this sigma is given by this matrix S is given by this, and now we define ourselves a matrix A, which you can write in various ways, but this matrix A is basically just given by this 2 by 2 matrix here, but we could also write it as epsilon U epsilon, and important for the proof, this is the same as T epsilon T inverse epsilon. And the statement then of this lemma is that for all weights k, that if we let this element 1 minus sigma act on this generating series of these symbols zk1, k2, then this equals the generating series of these products p, k1, k2, where we let act this element in the group ring here, minus this rk, which basically just has these single zk as coefficients, where we let this element here act. And before I give the proof of this lemma, I want to give somehow an interpretation what this actually means. So first, what is Z? So first I want to understand the left-hand side. So Zk of sigma. So sigma is a negative identity matrix. So what this is, xy. So this is just zk minus x minus y. So and because zk is a homogeneous polynomial of degree k minus 2, this is just minus 1 to the k zk xy. Therefore, if I have this expression here, so I let the identity matrix act on this, which doesn't do anything, minus this part here, we see that this zk, where I let this act, is depending on the parity of k. So if k is even, we see that this term, here is 1, and therefore we subtract just zk from zk, so this is 0 if k is even. And if k is odd, it's 2 times, not zeta, zk xy. K is odd. So depending on the parity of k, if k is even, then this part here is 0, and then this lemma gives a relation among these elements p, k1 and k2 and these single zk. And if k is odd, then the left-hand side is basically just the generating series of this zk1, k2, and then the statement is that zk1, k2, if k is odd, can be written as a linear combination of these symbols p, k1, k2 and these single z. And this So these two consequences of this lemma we will consider separately, but this odd weight case is usually known as a parity result for multiple zeta waves. And also I want to interpret this factor 1 minus delta here. So what is 1 minus the delta? So if we consider, so this should be now this fancy p, 1 minus delta, you see what this basically just does is, I have 2 times. So here I would have the generating series of pk1, k2. Oh, and here I should write xy. And here I have k1 minus 1 and y k2 minus 1. And what this action just does, if you, oh, maybe I should also recall delta. So delta here, so it just gives a minus sign in the x variable. So let me recall here. And therefore, if I subtract this from this pk, where I put a minus sign in the k, what it does is it erases the odd parts, and therefore this thing here is just the generating series of this pk1, k2, where the first entry is even. And of course here, sorry, this is j and k minus j, where k is the sum of k1 plus k2. Okay, so this part here is basically just these p k1, k2, where the first one, this k1, is even. Okay, so let's prove this lemma here. So prove. And maybe we should also take this down here. Well, without this stupid bracket here. Okay, so here this is a relation we have for these elements in the formal double zeta space. So this was the definition, and this is the only ingredient we can use. But first, what we observe is that if I take a cube, maybe this I also need. So A is this matrix here. So if you multiply this matrix here 3 times with itself, then you see this is exactly sigma. So in other words, this is a negative identity matrix. So this is the relation between A and this sigma appearing on the left-hand side here. So now we want to rewrite these equations here. So first, this first relation here states that zk, when I let epsilon act on this equation, so this part here, then if I bring this on the other side and also this 1 times on the other side, the statement is the action of epsilon on zk is minus zk plus pk minus rk. And here, if I would act with the inverse of t, then this part here becomes the identity matrix, and here I have epsilon t inverse. So the statement is that if I let so here I have t epsilon t inverse. So the action of t epsilon t inverse is minus zk, because here I now have t times t is t inverse. So if I put it on the other side, it's just minus zk, and plus p t inverse. So the action of epsilon on this zk is minus zk plus this. The action of this matrix on zk is minus zk plus this. And now, what is the action of A? So here now you see that A, you can check, is just this matrix here times this epsilon here. So if I want to see what the action of A is on this thing here, where this is zk, where I have the action of this, and then I take the action of epsilon, because this action is a right action. And then I can first use this equation here. So this is minus zk plus p t inverse, where I still need to act with epsilon. And this, now I can use this equation here. So if I let epsilon act on zk, it's minus zk. So here I get a plus zk. Plus, and now I need to also add these things here, but because of this minus sign I need to subtract. So I get a minus pk. So I have this p t inverse epsilon minus 1. So this minus 1 comes from there, plus rk. Plus rk. Okay. So therefore, the action of A on zk is zk plus something. And let's call this something, give this a name, for example kappa. Then we see that the action of A squared is, well, it's the action. So if I apply again A here, then I get this. So I get zk plus kappa. But I also have this kappa with the A. So this is zk plus kappa 1 plus A. And therefore, if I apply it again, zk A cube, I have zk plus kappa 1 plus A squared. And this is almost the lemma, because here now this kappa is rk and this thing here, so this gives exactly this part there. And here on the, so first again here the observation asks the A cube is sigma. So therefore, if I bring zk on the other side, I have a sigma minus 1. So if I multiply it by minus 1, I have the left hand side here. And here this rk comes from this there. And here, well, there's an, so we need to let this act on this. So, but by direct calculation, you can check in the group ring. So this just means you need to multiply out matrices. That if you would apply this to this there, so this is just multiplication in the group ring, then this is exactly minus 1 minus delta A1 plus A plus S A squared. In other words, this exactly gives the element here. Okay, so this gives the proof of this lemma, and one can see that using this group action, it's actually quite a simple lemma, because basically what we do is just multiplying 2 by 2 matrices with each other. But we will see that this actually gives a really nice result. So first, let's consider the case when k is odd. So as I said, in the case when k is odd, the left-hand side, where did I write it here? So if k is odd, the left-hand side in the lemma is just 2 times the generating series of these zk1, k2, and then we can divide here by 1/2, and we can also see that this part here is 2 times these products with the first entry even. So basically this part here is then just the products with even, and because this 2 cancels out with this 2, and then we have this part here. And therefore we could consider the coefficients of this equation if k is odd And what we get is this statement here, the so-called parity result. So for odd weight k, any zk1, k2 can be written as a linear combination of these elements p, where the first entry is even and the second is odd, and this single zk. And we can even get an explicit formula by considering the coefficient of x to the k1 minus 1 and y to the k2 minus 1, which states then that this zk1, k2 is given by this explicit linear combination of this pj k minus j, where j is even and k is just the sum of k1 plus k2. And then you can also work out, by using some binomial coefficients identity, that the coefficient of this zk is just given by this thing here. So for example, we get the formulas that z21 is just z3, because this part here cancels. z12 is given by this. And yeah, so you see that at the beginning I gave this table here for relations in dk, and the statement was that in odd weight these also here these zk and these products give a basis, and this follows now from this. At least we can see that these generate our space, and because the number of these are exactly the dimension by dk, we actually get a proof of this dimension formula here, which we will do in a second. But we see that these explicit expressions of these double zk1, k2 in terms of these p's and these single z's follows now exactly from this parity theorem. Okay, and here are more examples for this theorem here. And now what I mentioned, with this we can also prove the dimension formula for odd weight k. So the statement is that the dimension dk for k odd is not just greater equal, but it exactly k plus 1 half. And furthermore, that these single z's and these products, where the first entry is even, they form a basis of our space, because this is just what we saw. But now we will also see that we can also choose a basis where we take zk and we take these these double zk1, k2, where the first entry is odd. And so the proof is, well, we already know that this dimension was bounded below by this k plus 1 half. So to show the equality, we just need to show that we can express any element in terms of k plus 1 half elements, and this is exactly what we did in the parity theorem. So this plus the parity theorem gives that the dimension is equal, so it gives an equal for the dimension, and also is that this set B1 is a basis. But now we want to show that also this is a basis, but this also follows from parity. So let me copy this down here. So maybe let's. So we want also, to prove this, we need to show that actually any pj k minus j can also be expressed as a linear combination of these z k odd even. But this we can so first notice that if this k1 is odd, then this part here doesn't appear. And also if we want to show that these so we include this zk in our basis, so to show that this can be written as some linear combination of these, we can ignore this part here, so we can actually also take this equation here. So this is now a modulo zk. So what we need to show is that we can invert this equation here, And therefore, if we would write these coefficients in a matrix, we need to show that this matrix is invertible. And I do this in detail in the lecture notes, but the main point is here that if we consider this matrix modulo 2, so the first observation is that if I have a binomial coefficient with m is even and n is odd, then, well, because this is just m over n times m minus 1, n minus 1, then if m is even and n is odd, then this part here is even, or well, it's divisible by 2, and here this is just an integer, and therefore this is also even. And therefore this matrix here, which has these entries, modulo 2, we see that this factor here, so k minus j minus 1, j is even, k is odd, and therefore this part here is even, and this is always odd. And therefore this vanishes modulo 2. And then you can see that modulo 2, that this matrix with these entries here is a matrix which has a form like this. It has 1 on the diagonal and zeros on the bottom right and something here. But this matrix is clearly, so this is modulo 2, because here the entries are just given by this. And this matrix is clearly invertible, because we see by this formula that the determinant of this matrix is actually odd. And therefore, we can write any of these pk1, k2 in the weight, in the odd weight case as a linear combination of these zk1, k2, where the first k1 here is odd, and therefore this also gives a basis for our space dk in the case k is odd. Okay, so, and yeah, so if we take the multiple zeta value realization, then these formulas, of course, also hold for multiple zeta values, where you replace these p's by the products of zeta values, and this by Riemann zeta value, and these double zeta values. So this just gives a proof of the fact that any double zeta value in odd weight can always be expressed as a polynomial in Riemann zeta values. Okay, so now the consequence of our lemma for the weight, for the even weight case. So again, if I go back here to the lemma, so if k is even, then we discussed that the left hand side here is just 0, and therefore we get a relation among p's and single z's, and this can be written down explicitly, giving this relation here, that this zk with this factor here can be written as a linear combination of these p's. So in other words, again, so now as the weight is even, if we take the zeta values, this means that the single Riemann zeta value, zeta k, can be written as a linear combination of products of Riemann zeta values. And of course here this j in this k minus j is smaller than this k, and therefore we get that we get the well-known fact that zeta 2k or 2m is always a polynomial in zeta 2. But also we get, for example, so this one example of relations in this space here. So what we can obtain from this is, for example, that P44 is 7/6 of Z8. So for example, this would imply that zeta 4 squared is 7/6 of zeta 8. But we will also see that with the other realization for Eisenstein series, that this will imply that this is also true for G4, that G4 squared equals 7/6 G8. And this is one part of the exercises you did before, where you proved a similar statement for the small g. But this will now follow also from this formula here, after we will prove that there's a realization given by Eisenstein series. And also one simple consequence of this lemma, of this theorem, is that, for example, Zk is just the sum of all even pj k minus j. Which again, if we take the zeta values for our objects here, this just says, this gives the classical a recursive formula for the Riemann zeta value in even weight in terms of smaller weight products of Riemann zeta values, which then implies that this even zeta value is a polynomial in zeta 2. Okay, and the analog of the dimension theorem we did for the odd weight, in the even weight case, the statement is that the dimension is exactly given by k half, and that the set of these z odd, that they give a basis. But this will not be a consequence now of this theorem here, because here we don't have z odds. But this we will prove next time. But I just wanted to give it here because we already state the statement as a theorem for the odd weight case. But yeah, this we will do in the future. But and this will also have some nice application after we introduce this realization in terms of Eisenstein series. And this is what we will do next time. We will start by talking about realizations given not just in a vector space A, but in a Q algebra A. And then we will prove some further relations for these realizations. And then we will actually introduce this relation given by these Eisenstein series for the ZK. And for the ZK1, K2, what we will obtain is some kind of so-called double Eisenstein series. And these PK1, K2 will basically given by the product of Eisenstein series. And then we will see that these statements in this formal double zeta space have some nice applications for modular forms. See you then.